幸好当时我们也是想
怎么样？你学车？这样。
Okay. I've got the video that's mostly done. Yes. Really about like I started I think so. I don't think I have fun. That's that. It's just space. Yeah. You need to work. There's some. Well, I want to make sure.
Alright, let's start. Okay, so a quick announcement. So I think homework 1 should be, the grades of homework 1 should be out, be able to see it. And if you have questions, please ask the TA. So I don't know if I have already told you this before, but each TA will grade 1 or 2 of the questions for the entire class. Okay, so you've got to figure out which TA graded which question, if you have specific questions about it. Okay, so I can actually tell you now. So which TA graded which question?
I think Mahishakya graded number 2, and then Ami
You can
graded.
look up in the email while I. Okay, so I will let you know about that in a little bit. Yeah.
Are you trying to post the solution document?
Yes. So, oh yeah, actually I forgot to do it. So can you just send me a reminder? Okay, so solutions will be out because it's already been more than 10 days. So that's no point.
If we have a question for the TA, do we just send it that email?
Yeah, you can always send it to the particular, so this Utah Albert TA at Google Groups. So if you have a question, you can broadly send it to this email address, or you can send it to individual PAs. So
Mahishakya graded 2, Amin graded 3, I graded 5, and Shravan graded 1 and 3.
1 and
3.
you already said 3.
Oh, Amin graded 4. Sorry.
Okay. Yeah. Thanks. Okay. So this is the order in which people graded. So these are the questions that specific TAs have graded. So if you guys have questions about the grading, contact them. And homework 2 is due this Friday. Alright, so today we've covered a reasonable amount of ground in the course, and I think we've covered some of the basic, what I consider as like basic materials. So I wanted to do a quick recap of what we've done so far, and and in the recap I'll also talk a little bit about some of the questions that's been coming up with respect to homework 2, and today we'll start a new topic which is called flows and cuts in graph, and we'll talk a little bit about that. Yeah.
So I want to post the solution handles. The solution one.
Yes. This is what somebody had asked. Solutions will be posted today or tomorrow. Okay? So if I don't post it by tonight, please send me a reminder. Okay, so that's for homework 1. Okay. Sorry. Alright, so I just wanted to do like a very quick recap of what we've done in the course. So just to give a sense, so we did 3 basic paradigms that we will use. They are some of the very basic algorithmic design paradigms. So I thought I'd just do a quick recap of what examples we saw. Okay? So the first one was divide and conquer. And the main idea in divide and conquer is that you have an instance of some problem. You break it up into sub-instances, you solve them separately, and then you combine the solutions together. Okay? And what we saw is that usually these sub-problems that you divide into, they don't overlap too much. Okay, and that's roughly how we distinguish between divide and conquer and dynamic programming, right? Where basically these sub-problems don't interact too much when you're thinking of divide and conquer solutions. Okay. And but of course that's just a heuristic. Okay. And the analysis is done by writing down a recurrence, right? So we always said that you figure out how much this division step takes, how much this combined step takes, and for the sub-problems you just write down a recurrence because the problem size will hopefully be smaller, and this is how we analyze the running time. And usually we prove the correctness via induction. This is as you would expect because I mean in some sense you assume that the subroutines return the correct answer. And you show that if they did, then you have a good answer to the whole problem. Okay. So this is the general idea in divide and conquer. And technically speaking, what shows up is how do you solve the recurrence, how do you do these proofs of induction. Right? So, and here we saw a few methods. So one which we saw a couple of times is this plug-in check method, where you just kind of plug in the value of t of n and keep doing this. Okay? And hopefully you'll see a pattern, and then you can prove by that. Okay, so this is something that we have said. And, we saw there are a few other methods also. Okay, so we also looked at this recurrence tree approach. Okay, and specifically the examples we saw of divide and conquer are, we saw merge sort. We started off with merge sort, and we looked at a slightly more non-trivial example of multiplying n-bit numbers, n-digit numbers. Okay, and there it was a little bit tricky to see how divide and conquer would do the job. Then we saw this very cute algorithm for median finding without sorting. Right? So you can find the kth smallest element in an array without actually sorting, and this would actually take this O of n time. Okay, so these are some of the nice examples that you see. Alright, so then we started looking generally at dynamic programming, at this paradigm called dynamic programming. And here this is also based on some kind of a divide and conquer. It's based on writing a recursive subroutine for your problem. But now you realize that if you think of this as a recursion tree, then many branches of the tree are trying to solve the same problem, okay, the exact same problem instance. Okay, and this is why we said that we store answers. You can try to store answers to all the sub-problems for which you've computed the answer. And this is the central idea in dynamic programming, and it works well if the number of distinct sub-problems is small. So if you think of the recurrence tree, if every time you're solving different problems, then you don't gain much, because then you have to essentially explore the whole tree. But if the number of distinct problems is small, then you will end up doing that. Okay. And the examples we saw of this are what we call the subset sum problem. Right? Given a bunch of numbers, you're given some target sum s, you want to find out if there's a subset of these guys that adds up to s. Right? And then we saw this coin change problem, which looks very similar, and this example of longest increasing subsequence. And so technically what you've got to think about is how do you write down the recurrence. Okay. And so it turns out that how exactly you write the recurrence determines the running time and the space complexity of the problem. Okay, so this is something I didn't stress too much on, but I'm going to give an example now, partly because there were a lot of questions about this coin change problem in the homework. Okay, so I just thought I would clear it up. I wrote it in the notes, but I thought I'd spend like 5 minutes on this. Okay. So, yeah, another thing that I told you is that in some sense what I have explained is kind of the top-down view of dynamic programming, where you say that you start off with the original instance you want to solve, okay? And then you divide into and then you write down the recurrence tree, think of the recurrence tree at least, and try to store solutions to what you need to compute. Another way you can think of is you can think of having the whole recursion tree, and you can try to compute answers to these subproblems bottom up. Okay. I mean, this is what will eventually happen even in a top-down approach, right? Because you will go down to the bottom, then you will compute some answers and so forth, but you can do it more explicitly. So that's, yeah, this is something where I wrote down in the notes as well. Okay, so see the notes for lecture 5. I actually have an explicit example of how a program using the top-down, bottom-up approach will look like. Okay. All right. So that's an overview. Okay. So I wanted to give an example of how you write down the recurrence determines the space and time. Okay. And yeah, the example is that of coin change. Okay. So again, recall the problem. You've got coins of k denominations. Let's call them d1 through dk. Think of them as di cents. Is the denomination of the coin. And you want to make you want to make change for s cents using the fewest number of coins. Okay. S is some sum. Okay. So the way we saw in class, which was basically because somebody had suggested this and I just went along with it, and it turns out to have a little bit worse running time than what you can get by a different approach. Okay, and that's something that I didn't explicitly do, it turns out. Okay, so I just wanted to recall what we did. Okay, so what we did is we said we were inspired by the subset sum type proof, right? So we said in subset sum, the way we did it is say either you use the first number or you don't. Okay? And this is the same thing we tried to do for coin change. Here it's not just about using once, you can use a coin multiple times. Okay? So we said let's define a similar recursive procedure. Let's define this quantity m of s comma I to be the smallest number of coins you need to make change for s using coins di and above. Okay, that is di plus 1 to dk. So the answer we want is m of s comma 1, because we have all the coins that we are allowed. Okay, and this is the quantity, which is the minimum number of coins you need to make change using di to dk. And we wrote down a recurrence for this. And so the recurrence basically says, let's assume you take j coins of type I, of denomination I, and you search over all possible j's. So search for j equals 0, j equals 1, so on until j times di, as long as j times di is less than I. Of course, there's no point going beyond j times di more than. Right? So you look at all 0 less than j less than this, and if you use j coins of type di, then the number of coins you use is j plus this recursive call, where now your I in the second argument is now replaced with I plus 1.
What's that first term? Min j?
Yeah, so it's min over all j ranging from 0 through essentially s divided by di.
So what is j?
No, I'm searching over all j, right? So minimum over all j within this range.
J's are denominator.
No, I is the denominator, right? So,
Sorry, I just.
I is the denominator. Yeah, and so this is like saying, it's min over min of all these numbers. The first one is m of s and I plus 1. This is when you use nothing of type I. Right? And otherwise you can use one thing of type I, in which case you would get m of s minus di I plus 1, 2 plus minus 2 di, and so on. So this is notation for that. So this is what we saw in class. Okay, so I think we wrote this down explicitly like this. So this is what you can write. But and this we said takes time, which is rather space. Is the subproblems here are basically defined by S and I. And then we said you could try to memorize all the answers m of s comma I, and this takes time, which is s times k. Because technically speaking, it's s plus 1 times k, because your s value, the sum value ranges from 0 through s, and the I ranges from 1 through k. So this takes time, which is essentially s plus space, that is s plus 1 times k. And the time to compute one of these things is, we said, is something like s divided by di. Right? The number of comparisons you make here is something like s by di, because j ranges from 0 to s divided by di. So this is the time it takes for computing this quantity, and you can always upper bound it by s divided by d1 or something, the smallest denomination. And so the time complexity, time for the function called m of s comma I is upper bounded by this, which is the same to this. Like and class. So it turns out there's an easier algorithm that you could have done for coin change, and I thought I did, but I don't think I did. Which is, you can just let. Alright, so you can just let f of s denote the minimum number of coins needed to make change for s. Okay, so without keeping track of a starting point I, you could just have a simple thing which says, okay, so f of s, I'm just defining it to be the minimum number of coins needed and there is no description here about what coins to use. Okay, so this is just the minimum number of coins. You can use all of them. And this is something for which you can write a straightforward recurrence, because how do you make s? If s is non-zero, if s is 0, of course, the minimum number of coins is 0. If s is non-zero, you have to use some coin. Okay, so you basically try all possible choices of the first coin that you use. Okay, so what you can do is you can say that f of s is less than or equal to 1 plus f of s minus di. This is an observation. You have an inequality which is for any I. Right? Because you could have made change for s minus di, and then you add the di coin, you get one way of getting s. Okay. And furthermore, you have that f of s. Then the best way of making change for s is one of these things, right? Because you have to use some coin. Okay. So f of s is actually equal to min over all I coins denomination size of 1 plus, this is equal to f of s minus di. Okay. So this is a very simple observation, right? Because it's you have to use some coin. So you search over all coins, and you use that coin plus the best way of making change for s minus di. And of course, you do this only for coins that are I such that the I is less than or equal to s. Okay, it doesn't make sense to use a coin figure. Okay, so this is something that I forgot to mention in class, but this is a very simple alternate algorithm for this. Okay, because yeah, so someone suggested the previous one, so I went with the previous one, but I did not mention this other. Okay, but is this one here? Okay, so here all you do is so now the space requirement is only S because you just store the F value. Right? Just store the F value. Okay, and the time is S times K because in each computation you are looking at min over the denominations and there are only K denominations. So this is how you would do this. So this is a very simple algorithm and it gives slightly better space and time. Okay. And yeah, so there is one difference between this and the previous algorithm, and it's actually nicer that you've seen both of them. Okay, so maybe I will say it vaguely because this is one of your homework questions, is that the second algorithm, okay, it is prone to double counting. Okay, so it is, so what you're doing is if I want to, in some sense, make change for S, it's, okay, and suppose my denominations are 2 and 3, and S is equal to 5. Then first I will make a recursive call for S equals 2, sorry, S equals 3 maybe, and then I'll make a recursive call with S equals 2. Okay, and here I will make a recursive call for S equals 1 and then S equals 0. I will get this either here. And so in some sense I will count a way of making 5 as 2 plus 3 and 3 plus 2 in some sense in different recursive branches. If you think about it, the first algorithm does not do this because you kind of pick how many you want of one coin first, and so you never actually end up double counting. Okay, so that's a subtle difference between these two algorithms. And this is actually, if you want to count the number of ways of making change and so forth, this difference actually important. Yeah.
If this one does more work because of this double counting, then why is the time and space?
That's a great point. Yeah, so it's just that the way we are bounding it is inefficient. Okay, so yeah, this is a great point. What he's asking is why are the time and space words for this, right? So there's actually two answers to this. So I mean, if you actually run this, I still think that the first one will do more work, but this one is making more use of dynamic programming. So it's leading to more of these common subproblems. And that's the reason this will actually end up being faster, because I still think that the previous thing will actually do a lot of functional evaluation. Okay. So there could be some instances where it is faster, but yeah, actually, now that I think about it, I don't think it will. If you run it, it will very rarely be faster than this. So this is actually exploiting the substructure in a much nicer way than the previous formulation. Okay, but that's a very good question because this is actually doing some double counting and stuff, but it is exploiting this common sub solution in a much better way. Okay, so this is so this is why I was saying that how you write the recurrence often is important in dynamic programming. Okay, and typically if you are reasonable, it won't be too important. Like in our two examples, they were kind of the same, but there's always so there is some dependence. Alright, so this is something that I wanted to say. And so the next thing we looked at were greedy algorithms, right? So the basic idea in greedy algorithms is that your goal will be to make a set of choices, okay, and you make them one at a time, and you make them in a myopic manner. Okay, so you always choose the best in each step, and hope that the final solution is reasonably good. So that's the general idea of greedy algorithms. And the reason they are very popular is because they are very easy to design. Okay, very often, if somebody tells you a problem, in fact, without thinking, you might come up with a greedy algorithm, and you might even be confident that it always works. Okay? Because you think, okay, I'm making the best choice, right? But sometimes, the best choice at the end may not be the same as the best choice at each point. Okay. In fact, yeah. So there was a question in the discussions about, why did our proof for spanning tree have to be so complicated? I mean, we're always adding the best edge. Isn't it obvious that you'll get the smallest tree? And the answer is no, because you always add the least edge at that point, but what you get at the very end need not be the optimal. Right? And in fact, we saw an example of that in this hiring problem that we saw, where you always add the set that's going to give you the most advantage. Okay? But it's not going to be, but this procedure will not give you the best solution overall. It will give you a reasonable solution, but not the best one. Okay? So this is, so often they are easy to design, but not so easy to analyze. Yes, in fact, coming up with counterexamples can sometimes be tricky. Okay? And but we know it doesn't always produce optimal answers. And these are actually the elements for which we saw the most examples. So we introduced this problem of matching gifts to children, which hopefully you guys are all much more comfortable with now because of the homework. And we saw an example of a scheduling problem. So spanning trees where the proof was actually kind of interesting. And we also saw this hiring problem, and this was the first example we've seen in this course about approximation algorithm, right? Because we proved that the greedy solution always gets you at least, has a cost that's at least 63% of the optimum cost. Okay? By cost, I mean value. So your goal is to maximize, and you will say that the greedy algorithm does not do too bad. So this is something else. Right, and another thing maybe I should mention is that when you encounter a new problem, greedy is probably the first thing you should try, and you should see, okay, then you will get a sense of why is this problem somewhat not trivial. Okay? Because it's very easy to come up with greedy algorithms. You can try and see, okay, why does this fail, and it will give you some more insight. Okay, and the next paradigm we saw is what's called local search. Okay, so this again very simple. Here, it's an algorithm that starts with some solution and just tries to improve. Right? So it's very optimistic kind of algorithm. You start with some solution, you try to see if there's a better solution by changing the solution a little bit. Okay. And these are try to improve by changing a little bit. And this is the little bit is why they're called local search. Okay, so you make some local changes here. And again, these algorithms are easy to design and implement as well. Often the running time is not great though, and because you may have to try changing solutions in lots of ways, and very often it's hard to keep the running time small. You might make tiny improvements in each step, and it could take a long time to converge. So that's the usual problem with local search. In fact, there's a very nice complexity class that's defined on the basis of local search. It's called PLS, for those of you who are interested in these kind of things. So there are some problems for which local search is not known to work in polynomial time. Okay? Like you can solve the whole problem in polynomial time, but if you try to do local search, we don't know how to do it in polynomial time. Okay, so that's class called PLS. And like Nash equilibrium is a famous example. So that's yeah, it's an aside. Okay, and so the other thing is yeah, it usually produces reasonable answers. Okay, so in practice, we care about yeah, so reasonable answers. And we said that gradient descent is the most common example of local search. So this is for optimizing convex functions over a convex field. All right. Okay, so this is a quick overview of what we've done with respect to like the basic like algorithmic design tools that we've seen. And then we started looking at graph algorithms, and the one we saw so far is one of the most basic graph algorithms. So I just did it for the sake of completeness because these are things you should know. So we looked at this question of shortest path, and the problem here is it's a generalization of like breadth first search. Now you have a weighted directed graph, and you're given some u and v, and you want to find the shortest total length path from u to v. Okay, so it's not the number of hops; it's the total length. And so the first algorithm we saw, it's commonly known as Bellman-Ford. Also, it was earlier invented by Schindler, so it's Schindler's algorithm. And the idea is you always maintain a candidate value for distance from u, which we call, and for a vertex w, we call this dist of w. It's the candidate value for distance from u. Okay, so if you really want, you can write a subscript u here. Okay. So what we start off with is some solution. Okay, so you can think of this some kind of local search, but not quite. Okay, so you start with some assignment. You could even start with just 0 for u and infinity for the rest, and this will still work. Okay. So, but we assigned it using breadth first search. So you can do whatever. And what we said is that you maintain this candidate distance of w, and you update these by first checking if this distance of w was bigger than distance from I plus length of w. Okay, so what this means pictorially is, so we want to think of, we are keeping track of some path from u to w. And every time we look at some edge I to going to w, and we check if you can somehow get a shortcut. Like, is the candidate path you had to I plus the length of edge I to w, is it smaller than the original path you had from u to w? And if so, you would update this, and you would update your candidate path in some sense. And you keep doing this for n iterations. Okay? So do this for every edge in each iteration, and do this for n iterations. And what we argued is that this will always find the right distance length at the end of n iterations. Okay, and the proof was very clean. It showed that if the true shortest path had k hops, then after k iterations of this algorithm, you will find the right distance. Okay? So this was a simple property that it was. And this is how we use this. This is how the analysis works. Okay, and the nice property about this algorithm is that it also works when the graph has negative length edges. Okay. And but of course, it should not have negative total weight cycles, because then the shortest path round is not very different. So this is something we saw last time. Actually, this algorithm is also the basis, maybe I should mention this, for using matrix multiplication in the context of shortest path. Actually, just out of curiosity, how many of you have seen this, know what I'm talking about when I say matrix multiplication for shortest path? Okay, so some of you have seen this. Yeah, so this is actually a very, this is a popular way of doing what is called the all-pair shortest path problem. Okay, where instead you don't want to you don't have a source u. Okay, but you want to keep track of distances between all pairs. And so it turns out there's a nice way of looking at this expression as some kind of inner product type operation, okay, where you multiply a vector with a vector. Okay, so this is an inner product in a different algebra. Okay, so there's a nice extension of this algorithm. Okay, so that's why people still study this algorithm, even though it's worse than extra. Okay, so one reason is that it also works when the graph has negative weight edges. It also has connection. I mean, it can be extended to this all pair shortest path, and then you can use all the tricks you know for matrix multiplication for this problem. Okay, so there are all these fast matrix multiplication methods, and you can use those tricks for this problem. Yeah.
Sure. Can you repeat why this iteration takes number of edges?
Yes, because you do this the shortcut checking for every edge. Okay, for every edge IW, you see if going to I and then going to W gives a shorter path than the candidate path you had to W. Okay, so for each edge you do this check. This is why it takes. And this algorithm really proceeds in phases, and in every phase it checks all edges. Alright, so that's Bellman-Ford algorithm. Right, so the other algorithm we saw is it's called Dijkstra's algorithm. Okay, so this is actually the first algorithm for shortest path historically, and the way it works, it kind of tries to emulate breadth first search. Okay, and so what you do is you try to maintain a ball of a certain radius around the vertex u. Okay, so this is how you try to think of this, and you always increase the radius slowly so that you add one more vertex to this ball. Okay, and this is the idea behind Dijkstra's algorithm. So the idea is to add one vertex to the ball in each iteration, and the way you implement this is you still think of it as having candidate disk values to each vertex, and you add the disk value that has the least among the vertices that you have not seen so far. Okay, and this is what I explained last time. And so it turns out that you can prove that this value will be the correct distance value. Okay, and this was a bit tricky to show. I remember we said suppose all the disk values so far were correct, and you're adding a vertex W that had the least disk value, and so we said that the two shortest path W could not have looked like this, because then this would have a smaller disk value, and this was how we proved this. Okay, so we didn't have that much time for this, but yeah, but I will include a reference to where you can find this proof. This is a very, yeah, this is such a, popular algorithm that you'll find links to this proof everywhere. Yeah.
I think you mentioned that there was a difference between this and spanning.
There's a similarity. Yeah. I should mention that. It's good that you wanted to put it on this slide, but I forgot. Okay, so this algorithm looks almost identical to the spanning tree algorithm, except in the way the disk values are defined. Okay, in shortest paths, you define the distance value as the distance to u. Okay, which is what you care about, right? I mean, in shortest path, you want to find the path from u. Okay. But in the spanning tree problem, the goal is just to connect everybody. Okay, so you define the distance of W to just be the distance from W to the smallest, to the closest point in the ball you're growing. Okay. And now the ball you're growing is not quite a ball in the usual sense, like the distance doesn't always increase, but it's still a set of vertices that you keep growing. Yeah. So, but implementation-wise, it's just like half a line of implementation. Instead of checking for this, instead of adding the edge weight, you just look at the edge weight. Okay, so it's very similar, and the running time is exactly the same. Okay, so it's two minutes. The analysis is rather different though. Here the analysis is much easier than minimum time. Alright, so that's so this is a quick recap of everything we've done in the course, and I feel that this marks a point where we've covered in some sense the basic design paradigms and some of the very essential graph algorithms. And so what I'm going to do next is I'm going to talk in this lecture and a little bit of the next lecture about cuts and flows and graphs. They're like rather different problems from what you've been doing. And then we'll talk about linear programming. So that's where we're at. Okay, so cuts and flows, and so this is where you have like a lot of interesting problems coming in. Okay, so what are cuts in graphs? So the general question, which is a very broad question, is you're given some graph, and your goal is to cut or remove a small number of edges so that the graph is disconnected. Okay. And how you define disconnected exactly will vary. Okay, but there are a lot of variants of this problem. So one goal could be you are given some graph. It could be directed, undirected, weighted, whatever you want. And you want to remove. So let's say I give you. Okay, I should call them probably S and T if I want to call the problem an SD card problem. Yeah, but so one variant of the problem is you're doing S and T. And you want to remove some vertices remove some edges, so that after you remove them, there is no path from S to T. Okay. So I drew the undirected version here, but there's also a directed version of the problem that we'll soon see, where you're allowed to at the end have a path from T to S, but you're not allowed to have a directed path from S to T. Okay. So that's the directed version of this problem. So here, so one question could be, what is the minimum number of edges that you've got to remove to disconnect S from T? Yeah.
I wouldn't see any weights.
Yes. So in general, this is a weighted problem. So you are given weights, and you want the minimum total weight. So as I was saying, the general problem has weights. It has probably edge directions, and so on. And you have some W1. So this is, we'll get to this exact formulation in a little bit, but I just want to give a sense of what kind of problems we're looking at. Okay, so the first one is you're given some S and T and you want to break the graph so that these two get disconnected. Okay. And historically, this is the version that was most well studied, and may one think of applications for this? Okay, apparently the story is that the study of this problem goes back to like World War II time, where they had these graphs that represented like the road network of Germany or something like this. They want to take out like the fewest number of roads, so that there's no way of supplies reaching from one point to the other. Okay, so this had many of these problems grew out from this operations research community that has a lot of military applications. Okay, so that's how many of these problems started. Okay, but of course now we know more interesting or less interesting applications depending on how you look at it. Okay, All right, so that's the SD cut problem. Okay. And there's another problem that's actually really popular, which is you want to. This is more for undirected graphs. Still assume there are weights, but it's an undirected graph. So you may want to break up the graph into two roughly equal sized pieces so that there are very few edges that go up between them. Okay. So this is called the sparsest cut problem, and so you want to So the key thing here is you want to break the graph into nearly equal pieces, okay, and you want very few edges that go between these pieces. And for this problem, any thoughts about application? Yeah.
It seems like, well, I'm not sure too, but certainly if you generalize it into K pieces, it seems like it would be kind of useful for like graph sampling potentially. And that way you can kind of, I don't know, maybe try and do like graph algorithms on smaller graphs without, while hopefully maintaining a lot of desirable properties.
Yeah, so what he's saying is quite right. So what he's saying is you can think of this as a divide and conquer strategy, right? Like you want to break up a problem into multiple pieces so that there's not much interaction between the pieces. Okay, so you can abstractly think of divide and conquer as trying to solve a partition problem. Okay? And there's actually very concrete uses of this. Like, in most of modern machine learning, you want to do problems on different cores, right? So you want to break up problems where you do certain computation on certain nodes, certain other computation on different nodes, and you want the answers to have very little interaction between them. Okay, so if you have, let's say, some kind of a neural network, you want to do certain processing in one machine, certain processing in the other. You want very little communication between these two halves. Okay, so this is why dividing equally is important, because you don't want one machine to do all the job. So you want to kind of partition work across machines. Okay, so this is used a lot in these kind of distributed computing type applications. In the old days, people also used to do this for VLSI layout, but I know nothing about hardware. So all right, so. Okay, and I should mention a different problem, which is not about cutting while removing a small number of things, but this is, you can think of it as a complementary problem. And so the goal here is you want to partition vertices into two halves so that there are very few edges inside. Okay. So you want as many as you can of edges that go across the partition. Okay, so this is called the max cut problem, and this is a little less useful in general, but it's used when you want to divide certain graphs into two halves where, in some sense, within each half there are as few conflicts as possible. Okay, so it's used in situations where you have sets of nodes that have some kind of conflicts. You want to minimize the number of conflicts in each piece. Okay, so it's you can also think of it as trying to color with two colors so that you have very few edges of the same color. Okay, so this is called the max cut problem. This has a lot more of theoretical uses than practical applied. Okay, so this is a very popular problem in theory. So a problem is popular in theory if it implies something about a lot of other problems. In case you're wondering what does it mean to be popular in theory. Right. So that's so this is called the max cut problem. So it turns out that something interesting is true. So apart from this particular problem, nearly any cut variant you can think of will be NP-hard. Okay, so these two are NP-hard. Many other variants are often NP-hard. Okay, so the first one is one of the few variants for which you actually have efficient algorithms. And we're going to see that in a little bit. And as I said, each variant has many applications. Okay, so let's. So the goal of today will be to study this problem. Okay, you're given an S and T, and you want to break the graph. You want to delete a small number of edges, so that there is no path going from S to T. That's the min ST cut problem. Right. So formally, the problem is the following. Okay, so you're given a directed graph with edge weights. Okay, and your goal. So this looks like the graph. So let's assign some weights. Okay, so this is S. So, yeah. No, yeah, I think this is by accident. So, you can very well have cycles. Okay, so you could have so yeah, so this is a completely general directed graph, and your goal is to cut, which is remove a small set of edges. Where small, I just mean the minimum total weight. So your goal is minimize the total weight of edges cut so as to disconnect it from. Because everything is directed, even the disconnection is in a directed sense. Okay, so you don't want a path from S to T to remain. You could still have a path from T to S. Right? So this will be clear, we can add that. So one way to solve this problem could be to remove this edge. Right? So this would disconnect. This would mean there is no path from S to T. If you wanted, you could also have done removing, I don't know if you can see removing these two. That's another solution, both of which have cost 2. There's plenty of other solutions that have higher cost. Okay, so this is the problem. Okay. Any question about the problem? So yeah, so one slide that I forgot to have is okay, so a little bit about the history of this problem, or what is known. And so it turns out that this is one of the few problems for which we know, one of the few cut variants for which we know polynomial time algorithms. Okay, so there is a poly time algorithm. mean, I don't know about you, but to me, this seems like a problem that is very difficult, right? Because you want to find a subset of edges to remove so that there is no path going from S to T, right? And this seems, I don't know, intuitively much harder than finding a short path or something like this, for which you can come up with an obvious algorithm, right? So this is, so this is one example of an algorithm that I think at least is non-trivial. I would not suspect that there's an easy way to solve this problem without actually trying a lot of things. So this is, for this reason it took a while. Right? So this has a polytime algorithm, and this was proved by 4 persons. This is in the 50s. The problem arose earlier, but then people didn't have an efficient way of doing it. In the 50s, these guys came up with an efficient algorithm. And it turns out that this is another example. Actually, we haven't seen any examples so far, but this is one example of problem where directed graphs seem harder to handle than undirected ones. Undirected. For undirected graphs, it turns out, let me first say what we know for directed ones. I think the best known algorithm is something like O of m times n. Okay, so it's the number of edges times the number of vertices. There's also some log factors hiding that. Okay, so this is one algorithm that's known. For undirected graphs, we know much better. So undirected. Okay, actually, undirected graphs you know a little bit better, but if you have unweighted undirected graphs, then we know algorithms that are just roughly something like n plus. Okay. So that's log factor. And we might see an example of this when we do randomized algorithms. Okay, so this was a breakthrough result in the 90s by David Carter, by 90s and the early 90s actually, 93 or something, I'm not very sure of the year, by David Carter. And he came up with a very clean randomized algorithm for this problem. Okay, so it's a really simple algorithm and it takes almost linear time. So this was actually a couple of papers. In the first one, he just observed this procedure, and the second one, he changed it to near linear. So that is something about unweighted graphs. And for a long time, people didn't know how to make this a randomized algorithm. People didn't know if randomization was essential. Okay, but what do I mean by randomized algorithm? It makes certain choices in a random way. Okay, and the only guarantee you have is that the algorithm works with a certain probability and the expected time is that. Okay, so occasionally it could take more time than this. Occasionally it could give a wrong answer. Okay, so that's what people knew. Okay, and so one of the big questions was if you could do this thing in a deterministic way, where the algorithm is always guaranteed to run in a certain number of, it's a deterministic algorithm. It always produces something, the right answer, and it runs in a certain amount of time. Okay, so this was only answered a couple of years ago. Okay, so this was 2015 by Mikhail Kovarup and what's he called? KLC Kovarup. Okay, so this was it's a very, very different algorithm than all the known algorithms for mankind. Okay, so this is it uses properties of the page rank algorithm and so on. Okay, so Mikhail Thorup gave a talk at Google once about this algorithm, and he said this is the first time PageRank algorithm has been useful. Yeah, so it is actually, I mean, theory-wise, it is true. In terms of theory, this is the first like concrete application of some result you get for page. So this is what we know. Okay, so in some sense, we know a lot for undirected graphs, and we know like really good bound. For directed graphs, it's much harder. I actually don't know what the best bound is for this, because there have been recent improvements on this front also. Okay, so yeah, I can check this, and I think it's something like to the 1.4, something like this. But yeah, I should check this before I think. So, all right. So this is the general history. So what I want to illustrate is that this is very much still, it's a basic problem, but it's still very much a topic of research. Yeah. Oh, always n is number of edges, and n is number of rows. Okay, and of course m lies between n and n. Okay, you assume graphs are connected, so this m is at least n. Okay. Alright, so what, so let me try to describe an algorithm for this. Okay, so we won't describe it in detail, but I'll just give you how it proceeds. And as I said, so the key idea, at least even in the old algorithms, is to solve a totally unrelated problem, a seemingly very unrelated problem. And this is called the maximum flow problem. Okay, so what is the problem here? Here, the question is, we are given a weighted directed graph. Graph interpreted as the edge weight of an edge as the capacity then find the maximum amount of flow. I will define all these terms in a little bit from given source to P to a sink P. This is called the source to, and this is P is called the sink. Okay. That respects all these capacities. That does not violate it. So it is an example. So you're given a weighted directed graph. So I want to think of two nodes S and T as being special. And the weights, I want to interpret them as the capacities for these edges. Okay, one way to think about it is think of the edge weight as the amount of bandwidth. If you think of some kind of a communication network, okay, so you have directed edges where you can communicate with V, and the weight of the edge gives the bandwidth. People are also motivated in terms of water pipes and the diameter of the pipe. So I think bandwidth is easier. Okay, so this is the amount of amount per minute that you can send. Yeah, if it's more convenient, you can think of water pipes and you have the diameter of the pipe telling you. It's like the capacity of that. It's the rate at which you can transmit along that edge. and you have something like this. And again, it's a fully directed network, so you can have edges all directions. Okay, so let me call these capacities 1, give some value, and so. So perhaps I should give a simpler example so that I can actually illustrate what the value is. So let me give an example that would be. Okay, let me give a slightly more example. Okay, so you have a graph. Yeah, forget this graph, it's a more general graph, but this is one that you can actually reason about. Okay, so you have S and T. S is the source, T is the sink. And the capacities, you should think of them as bandwidths of that particular edge. And you want to send some data from S to T. It's a communication network at the largest throughput possible. Okay, so if you had this graph, if you chose to send like 10 units along this and 5 units along this path. Okay, so you've got 2 paths, right? You could choose to send 10 along that and 5 along this one, and now you would have a throughput of 10 plus 5, 15. Okay, and you would not violate any of the capacities, right? So this is one way to do it. Another way, which is a little bit better, is you send 10 units like this, and okay, sorry, in this case, maybe I should have swapped these. Okay, so I wanted to illustrate non-trivial solution. Okay, so earlier solution still holds, like you can send 10 units on the top and 5 units on the bottom. That's still a valid solution. But now you can do something a little bit trickier. You could send 5 units along this path, and now you can send some flow along this path. Okay, where you go, maybe I should draw the paths of different colors. By the way, the first solution here, I'm just sending 10 units along the top path and 10 units along, 5 units along the bottom path. Okay, so that solution, just to clarify, it just looks like this. Okay, and it achieves a value throughput of 50. Okay, while the next solution I want to describe is something where you send 5 units like this, then you send 5 units like this, and you send 5 units like this. Okay, so 5 here, 5 here. Okay, it's still 15. Okay, I want to do something better than. I guess in this case you can't do better than 15, but okay, I should have drawn a better example. Okay. But this is another solution that achieves 15. Okay. Let me not change the example to 29. People get confused. So this is another weirder way to achieve a flow of 15. Okay. Note that you're not violating any capacities in doing this. So that's that, right? So this is the problem. Okay, so and the motivation I gave is itself an application, right? So this is often used in communication networks where you have channels with certain capacities, which are basically these edges, and you want as much throughput as possible, streaming a video or something like this, and you want as much throughput as possible. So this is one problem. And so it turns out that there is a very interesting connection between the cut problem that we wanted to solve and this flow problem. Okay? And in fact, all algorithms we know, not all algorithms, but the first algorithms for cut actually go by solving this seemingly unrelated problem. Okay? Because there we wanted to disconnect from UAV, and now you want to send a lot of flow from UAV. Okay, so yeah.
So what would be the maximum flow of that it would be 30?
In this graph, for this graph you mean?
Yeah.
So in this graph you cannot have a flow of more than 15, it turns out. Can you see why? Sorry?
Oh.
Yeah, it turns out 15 is the most flow you can send. The reason is that there's only 15 units of incoming edges to T. You can't send more than that. Right? So for this trivial reason, you can't have more than 15. But it turns out that this is exactly why it's related to the min cut problem, this kind of reason. so we will see why. Okay, so what are algorithms for flow? Okay, so it turns out, so I won't have time to do this today, but I will only have a connection between flows and cuts that I'll do today. But it turns out that natural greedy algorithms do not work. Okay, so the flow problem seems much more doable, right? Because you want to say that you send some flow, try to see if you can improve. Like in this example, you could have said, oh, I'm going to find one path, I'm going to see if there's more paths so that the capacities are not violated, and keep doing this. Right? So it seems more amenable to attack. Okay, so it's natural approaches exist. Right? So just send some flow. If you want, you can reduce capacities appropriately. And then find another path if it exists. So this is one clean incremental algorithm that you can write. Right? So see if there's a path, send whatever flow you can along that path. And now see if there's another. Now change the capacity values, because if this flow if you sent like 5 units of flow, then like think about this example. Right? If you first did this 10, now you can't send anything along this edge anymore, so you would have to reduce its capacity to 0, and you have to keep doing this. See if there's another path and so on. Okay, so this approach turns out does not work. Does not work in the sense that it is not optimal. Okay, so we'll see examples of this in the next class. But this is one of the few problems for which, some sense you can fix solutions. Okay, so you can do backtracking in a systematic manner. Okay. Okay, so it's one of these problems in which you can start with any solution and you can try to see if it can be, if you've made the wrong choice, and you can correct previous choices in a systematic way. Okay, so this is one way to think about what's called the four full Pearson algorithm. Okay, so this is Yeah, so this is a very nice algorithm. So this is, you will see it. It's very rare that you can do things like this. Okay, but it's possible for flows. Okay, but in the minute or so we have, let me try to tell you a one-line connection between the max flow and the min-cut problem. Okay? So there's a one-line connection and there's a one-lecture connection. Lecture one we'll see next time. Okay, so the one-line connection is, I want to claim that the value of max flow is less than or equal to the value of the min cut. Okay? And in particular, what I want to say is, if I take any cut that separates S to T, S and T. Okay, so a cut is a collection of edges that you've decided to remove, so that there is no path from S to T. Like this. These are the edges that you've tried to remove. I take any cut in the graph, okay, that ensures that there is no path from S to T. I want to claim that there cannot be a flow of more than the value of this cut. You guys see why? I mean, intuitively, it's kind of obvious, right? In the sense that we want to send flow from S to T using a bunch of flow paths. Okay? And each flow path, it goes through some of these edges. And a flow path cannot avoid all of these edges, because otherwise this would not be a valid cut. Okay, so if there was a flow path that did not use any of these these three edges would not form a valid cut, because removing them wouldn't disconnect S to T. Okay? So any flow path must use some of these edges. Okay? And we know that the flow must respect capacities. So the total amount of flow going through an edge has to be less than the capacity of that edge. So if you so in particular, the total value of the flow cannot be more than the sum of these edge weights. Okay, than the sum of these edge weights. Okay, so this is a very short connection as to why no flow can be more than the value of any cut, which is why the value of the max flow is less than the value of the min cut. Because you could have chosen the best such cut, and our argument still holds for that cut. So that's the very short connection.